we are happy to have Lutz talk today about degree-restricted random processes, which are far from uniform, or maybe not, who knows.
Thank you very much. Thanks for the organization for putting together this nice workshop and for giving me the chance to speak here. So everything I'm going to talk about today is joint work with Mike Malloy and my PhD student Erlang Sawyer. And the basic idea is I'll show you what I think is the simplest possible way to generate the graph with a given degree sequence. And then we can ask the strategic question, what can we say about the distribution of this graph? Is the distribution of this graph like close to uniform or not? Okay. So to put this maybe a little bit into context, let's maybe just focus first on the case of regular graph sequences. Okay, and so suppose you give an undergraduate student the task to generate something like a random d-regular graph. They'll most likely not come up with a configuration model, something like this, which is kind of fine-tuned to generate the uniform distribution, but most likely they'll come up with, I think, the following random greedy approach. So you start off with an empty graph and vertices, and then you just step by step try to add as many edges to your graph as possible without violating this maximum degree constraint. Okay, so in each step, add a new edge which does not violate the maximum degree D constraint. And this is such a natural algorithm. It was studied already in the 1980s. If you go back to it, in the mathematical chemistry literature, it was suggested there as a model. And in the early 90s, Wormald and Rutchinsky showed that actually for fixed D, this graph, in some sense, this process is good in the sense that it actually finishes with a d-regular graph unless there's some parity constraint which prevents you from doing that. So in that sense, this is a graph, a process which generates a d-regular graph. But the question now is, what can we say about the distribution? In particular, is it similar to a uniform random d-regular graph or not? Okay, and Wormald conjectured in the late 1990s that for this d-regular case, it actually should be similar to a d-regular graph, and the notion of similarity he uses contiguity. Okay. And what I want to discuss in this talk is kind of a variant, because look, in this process, we just say every vertex should have degree at most d. But of course, when we think about degree sequences, we can just say every vertex vi can have a degree at most di, and then we can ask the same question. And what we can show is that if the degree sequence is not quite regular, there's some irregularities, then we can actually show that these things are different in quite a substantial way. That will be the main result I want to talk about. But let's just be sure that we're all on the same page how this process looks like. So here's a small degree sequence. So we have 3 vertices of degree 2, 2 of degree 3. And now what we do is we step by step add these edges to the graph. So we don't allow here for loops or multiple edges. And the thing I want to just illustrate here is what happens at some point, these degree constraints will be satisfied. So this vertex has degree 2. And then the way to think about it is this vertex becomes inactive. It no longer plays a role because you can never, ever connect a vertex here to this guy. Okay, so this kind of shows that already the set of vertices to which I can actually add edges kind of changes over time. So we run this process until the end, and then we want to understand what is the distribution we get at the end. As I already told you, there's this result by Warnke and Rutchinsky, which actually works for all degrees which have, say, bounded maximum degree. So the maximum degree is a constant. Then what they proved is, again, that it actually works in the sense that in the end, every vertex vi will have degree di if your degree sequence is graphic, meaning that you actually can generate such a graph. So now, to rephrase this question, is how similar is now the output of this degree-restricted process to a uniform random graph with a given degree sequence? And depending on which hat you want to put on, you can ask this question in many different ways, but these are essentially all the same ways. So you can ask, okay, is there a way, can I actually distinguish them? Okay, can I do it algorithmically? If you have more the statistics perspective. If you ask maybe more from combinatorial probability, you're probably interested in what can we say about the typical properties? Are these graphs kind of the same with respect to typical properties, which leads to this notion of contiguity, which says that any graph property that holds with one model with probability tending to 1 will also hold in the other model with probability tending to 1. If you're more interested maybe in algorithms for actually generating, for example, approximately regular graphs, then you can also ask, well, does this process work in a sense that it actually gives me something that's close to uniform, which would be kind of nice because admittedly, this is kind of the easiest way you might think of generating such a model, and it's quite also efficient to implement. Similarly, maybe if you ask a strategic question for modeling, you know, in physics, there's this principle, we want to find the simplest possible model that can explain something or that works. Then again, it kind of motivates why you might want to study this, because this is really the simplest thing you can imagine. So what is our main result here? So the main result is that in some sense, if the degree sequence is not nearly regular, then we can distinguish them in a very strong sense, that I can give you a certain statistic that you can compute for each of these that you can compute. And depending on which model you are, with high probability, they will be in different ranges. So you can actually tell just by looking at a specific statistic, which model the graph actually came from. So now what does not nearly regular mean? Here, so the cartoon version is like no degree appears more than 99% of the times. Of course, you should really think of this as 1 minus epsilon fraction of the time. Okay. So that shows in some sense that this degree restricted process does deviate quite significantly from the uniform distribution. So you might ask yourself now, okay, what kind of statistic would you look at here?
Sorry, I'm missing your definition because use the microphone.
I don't understand your definition of not nearly regular, because this sort of, suppose they would all be equal. And then that does not say no degree appears.
So if it's irregular, then it would appear 100% of the time, and I want to rule that out. So I want to rule out that 1 degree appears like 99% of the time, like 1 minus epsilon fraction of the time.
Okay. Okay. Sorry.
Mm-hmm.
And should we understand that the dn is forcing your graph to be not regular or something?
So this is our assumption here, that if we look at any such degree sequence which is not regular, then this conclusion holds. So that's our assumption. So we don't make a statement in particular about regular degree sequences here.
I understand, but just by choosing a sequence to be not really regular, you're forcing the graph to be not regular. Is that how?
Yes.
By regular, it means all have the same degree.
Yes.
So that's my definition.
In particular, half of the degrees can be 2, half of the degrees can be 1.
That's right.
Okay.
So let me just tell you how the statistic looks like if, say, you have a reasonable amount of vertices of degree 1. Okay. So imagine now your degree 1 vertices are somewhere between 1% and 99%, and you should really think of it as at least epsilon n and at most 1 minus epsilon n. Then the edge statistic that we're going to look at, it turns out it's enough to look at the number of 1-1 edges. So by 1-1 edges, we mean edges where both endpoints have degree 1. Okay, and so if you look at this surprisingly simple statistic, what turns out that they actually differ in these two models. And one thing I just want to remark is that in some sense, this reinforces this idea that the degree sequence of a graph is not everything, because this really shows the fact that we generated this graph with this degree process using this evolution, using this process by adding edges one at a time, we do get other structural properties. So just saying the degree distribution captures everything is a big oversimplification. And here is a very simple example which tells you that some really key properties can change just by the way you generate the graph. Okay, so that's one interesting point I want to mention. And the other point I want to mention here is that when you try to prove such statements, another kind of difficulty is how to get the foot into the door in some of these questions, because I mean here we have a uniform random graph and we have this configuration model underlying there, and so there we really understand extremely well what's going on, in part because this configuration model for generating this random graphs with a given degree sequence has these nice properties which you can think of as like some form of exchangeability. You can kind of open up the graph from any point where you want, and the order in which you look at things does not matter. But if you look at this this process, this is like a very different story, because kind of the process has inherently some time evolution that's moving the process forward. So if you just want to even understand how does locally some neighborhood look like, it's quite a complicated thing to analyze. Okay. And in the bootcamp, there was mentioned one technique how to potentially study such processes. You can, for example, track the number of 1-1 edges at each step in the process, for example, using the so-called differential equation method, which would give you a prediction of how many 1-1 edges there are in terms of the solution to some differential equation. Okay. And this is one possible way one can try to prove such results on this level of generality. And in particular, if you give me a particular degree sequence, I can put it in the computer and then confirm, yes, it indeed differs from the configuration model. But I don't know how to implement this argument in general, like how to control these differential equations enough to make such a statement. So that's kind of still one open problem in this background. And that's why we use a different technique, which I think is not used so much in the context, or maybe I don't know of an example actually where it has been applied previously to a stochastic process that is not uniform. So the method we're going to use is a so-called switching method, which has been quite successful in analyzing particular random graphs with a given degree sequence where these degrees are very high. Because then you can no longer do this trick of the configuration model that the condition on the configuration model being simple, because the probability that the configuration model is simple is just tiny. Are there more questions about the model or the kind of result we're shooting at? Yes?
Just to check with my intuition, I prefer maybe asking about the mic.
I can repeat the question.
Yeah, thanks. So I just want to check that my intuition is correct. So I would assume that the DN process results in more 1-1 edges than the truly uniform random DN graph, or
Yes,
am I
that's
wrong?
right.
Okay, thanks.
I'll show, the next slide actually, one reason why this might be true.
What was the question?
Oh, sorry. The question was like, the guess was he was guessing that maybe this process generates more 1-1 edges than the uniform random graph. And what I said was that basically this was something I wanted to discuss on the next slide, maybe one intuition why this might be true. This is not the way we prove it, but some way you might think of it. So we discovered this originally by doing this differential equation approach, but so here's one way, sort of a cartoon, how you can think about this, okay? So here, let's just work with the configuration model. I mean, we're working here with degree sequences of bounded maximum degrees, so we can just as well think of the configuration model. And now, the way I like to think of the configuration model for each vertex, if you have can have degree 3, you have kind of these 3, I don't know, you either can call dangling edges, stubs, or I guess everyone has their own favorite term for this. And if you now run this sort of dynamic version of the configuration model, then each step you connect 2 of these dangling edges uniformly at random from all possible choices. Okay. And now you can check. So how many ways are there to connect, for example, this 1-1, these 2 vertices of degree 1 down here? There's one possible way, right? But up here, if I look at, for example, these 3, there are 9 possible ways to connect up here, right? So connecting these 2 vertices in one step is much more likely than this one down here. Okay, so you have some kind of preferential attachment mechanism sitting in the background with respect to your unused degree. Okay, but if you now look at this DN process, the DN process has like a different mechanism that drives the thing, right? Because remember, how is it defined? You just add any possible edge here to the graph that does not violate the degree constraint. Okay, and so what that means is that the probability of adding this edge here versus the probability of adding this edge here is actually the same in one step. And so this immediately tells you that at least in one step here, the probability of adding this edge down here is much more likely in the DN process compared to the configuration model. But note that this is really we're just looking at one step here. This does not yet say anything about if we do multiple steps, but I think it does drive the point home that here we have something uniform that's working, and here's something preferential. So it's plausible here that we actually do get more of these 1-1. So what is the kind of result that we prove? So we already said we're looking at these 1-1 edges where both endpoints have degree 1 in this example where we have lots and lots of degree 1 vertices. And so in this case, what we show is that basically these 2 random variables, depending on which graph model you look at, live in disjoint intervals with high probability, actually with exponentially small error probabilities. Okay, so we show that his G subscript Dn, this is the uniform graph that lies here in the middle, that's concentrated around this expected value, and there are many ways to prove it. You can prove it using first and second moment method, or you can prove it using a Zuma-Höferding inequality, or you name it your favorite method. So that's the standard part of the argument, to show something configuration model that's vanilla argument. And so the key question is how to show that the other process lies somewhere else. How can we get our hands on that? And there I said, in principle, one can try to use this differential equation technology, but there, seeing we don't have enough control over these differential equations. So in some sense, might be weird on first sight because you reduce it to an analytic problem. We just don't know how to solve the analytic problem. So we need something else. Yes, it's the same. So I mean that. So the question was if
the question was that by x11g you mean number of isolated edges.
Yes.
Right?
Mm-hmm. So the point here, this will have degree 1, this will have degree 1. But if you look at more general degree sequences, then it's not just isolated edges. You need to look at more complicated things. It's just this particular case where you have many vertices of degree 1 where this works. I'll maybe say later how the general thing looks like, but this is a little bit easier to explain what's going on. Yes, that's right. So here we assume always that the maximum degree is some constant. So yeah, we did not try to optimize too much for the maximum. Maybe you can allow some small power of log. I'm not sure. So let me try to give you some glimpse of what this switching does. Okay, so the whole point is somehow you want to change your perspective. So why has this method been very successful for analyzing, for example, uniform random graphs in regimes where the configuration model does not work? Okay, so let me see if I can put it here. So if you think of some classical switching argument, how would that look like? You would, for example, try to understand how does the probability that your uniform random graph generate, so sorry, this is 1, I think here. So if I compare the probability that this is equal to L versus the probability that this is equal to L plus 1, in the uniform case, the nice thing that happens is that the renormalizing factor kind of cancels out because we have a uniform distribution. So the total size of the universe that you divide through, that kind of just goes away, right? Because this here is just the number of these, say, dn graphs. So this, I mean, the number of graphs with the degree sequence dn, such that x11 of g is L, divided here by so this is now this kind of in the uniform setting, looking at ratios reduces yourself to a counting problem, and then you have to figure out by the switching technique, which I'll just mention a little bit about, what this ratio actually is. Okay, so the key point is it bypasses the need to understand how many graphs your sample space actually has. Okay, so that's, for example, a problem for d-regular graphs that was only solved a few years ago, how many d-regular graphs there are for all possible d between like 1 and n. And so this kind of really bypasses this technical difficulty that this number is difficult to understand. And here we want to apply a similar idea in the context of this stochastic process. But now, of course, the process we're looking at is not uniform. Okay, so the simple canceling out that happened here in the uniform model, we cannot expect that to happen. So we have to implement this idea slightly differently. Okay. So what underlies this kind of technology? It's this definition here, which I just give by example. Okay, so the idea is the following: I give you some graph, and you identify some very particular configuration. So here you identify here 2 vertices of degree 1, which are connected to a vertex of degree at least 2. Okay, so this is like a vertex of degree 1 connects to a vertex of degree 2, and now you do some kind of local perturbation operation, which I think there are also some similar ideas in the context of Stein-Shen method. So what you do is you replace these 2 edges just by these 2 edges. Okay, so you go from a situation where the graph stays the same, except as these edges get deleted and these guys get inserted. Okay, so you just keep everything the same except for these few edges. And now you want to understand, how does this local perturbation, what effect does it have on your probabilities? And the key point here is that in this graph here on the right, you have one edge more than on the left, but everything else stays the same. So the degree sequence stays the same. It's just that with respect to our key statistic, the number of 1, 1 edges, this graph has one edge more. So that's the thing we want to understand. In particular, what is this ratio now? What is the ratio between seeing this graph and this graph? Okay, note that in the uniform model, this would just be 1, this would just be the same, but we're trying to find this slight bias. What we want to prove is that this graph is a little bit more likely than this one. If we can show something like this, then we're in very good shape of proving actually that this process really prefers these 1, 1 edges. And so, as I already mentioned, this classical idea of looking at these probabilities and then the normalizing factor cancels out, we cannot quite use that here. So we have to look a little bit more carefully into what's going on. And so what we do is, you first observe, okay, this thing that you get here is no longer uniform, or that's what we believe. And in particular, when you look at what's the probability of getting one of these graphs, actually, what happens is there are very many different trajectories of the process that can give you this graph, because kind of the order in which you insert these edges matters. Remember at the beginning, I showed this example that certain points in time, certain vertices become kind of like inactive. Their degree is filled up. And so these moments when this happens really influences the probabilities in your process. So depending on which order you look at the edges, you get different probabilities. So kind of what we do, or what the idea is now, let's just look at it kind of one step even deeper into the process. We kind of look on the level of trajectories of these edge sequences and now try to mimic this idea here that comes from the classical switching method.
So I don't quite see why in the uniform model that would be the same, because if the probability of having L11 edges is the same as having L plus 1 L11 edges, then the probability of an infinite 1 edges is the same as having 0.
Okay, so what I was referring to is that the probability that you see this graph and the probability you see this graph, they will be the same.
I see, but you haven't explained how to calculate this ratio.
No, this will come on the next slide.
Even for uniform.
Okay. I will mention later basically how you also do this for uniform, but the basic idea is, again, you use this switching operation and you ask yourself how many ways are there to go from here to here, because you can kind of imagine you do some switching to take a graph with L to a graph with L plus 1, and you then have to calculate how many ways is it for one graph to go from here to here and the other way around. And if you understand what these ratios are and some nice things happen, you can actually out of that squeeze these probability bounds. So the next slide might look a little bit scary on first sight. So, but let me. Oh no, this is okay. 2 slides away. So this one is still fine. So this is the key lemma that I mean by switching that we really want to prove. We want to prove the degree restricted process favors this graph over this one, and the reason being this graph has one more edge more than the graph on the left. Okay, that's our goal. And so the thing that turns out to be tractable, initially it looks a little bit as if you have no chance, but we just expand out this probability that you get a certain graph over all possible edge sequences that can give you this graph. So it's a gigantic sum, okay? It's a gigantic sum. And then our goal was later to understand what happens when we perturbate these guys here. And it turns out to be surprisingly tractable in this context, I must say. It's really very nice. And so now this is the picture I alluded to. So let me try to explain what's going on here, okay? So beforehand, I said we want to compare with what probabilities do certain graphs appear. And now we want to kind of compare with what probabilities do certain edge sequences appear. So imagine I have some edge sequence sigma, which tells you exactly in which order the edges of a certain graph in which they arrive. And so what we're going to do is, for some technical reasons, we have to pair up 2 things. We compare the probability that certain 2 edge sequences appear with 2 other edge sequences. And now the question is, what are these edge sequences and what does it mean? Okay. And so recall that we did this switching operation up here, which says that replace these two blue edges by these two red edges. Okay. And so now suppose that we know certain points in time where these edges A, B, and X, Y, where they occur. Okay. So to make everything symmetric, first of all, I say let's just really fix these times here, okay, for the moment. And I mean, for symmetry reasons, you should consider when AB occurs first and XY second, or the other way around, where XY appears first and AB second. And then you kind of exactly want to do this switching operation. Now you want to put exactly at these spots the edges from your switching. So you want to replace ABXY by AXBY. Okay. And again, you have both options. One edge comes before the other one or the other way around. Okay. So if you fix the positions where these two edges should appear, these are kind of all possibilities to complete this switching picture up there. And the main point is that actually, if you write all these things down as ratios, you can actually prove an inequality of this form, that the left-hand side, which corresponds to these edge sequences to this guy, is actually more likely than the right-hand side, which correspond to edge sequences from here. Okay, and I'm not hiding anything. This is a real inequality. There's no little O of 1, there's no epsilon, whatever. This is just an inequality that's always true. Okay, and the advantage is you prove this by looking at ratios. This way, we don't really have to calculate the full probability that you see a certain trajectory, which is actually quite hard. Moreover, the thing that I want to mention here mainly, this is still consistent with our heuristic. Because remember, this blue guy here has one edge more than the red one. And the inequality is going the right direction because these two sequences correspond to this graph over here. Okay, so far everything is kind of consistent with what's going on. But the main point I want to bring across here is that there is a way to take these ideas from the switching method and try to think of them in terms of what does it mean in terms of trajectories of your process when you go kind of one level down. Of course, this is not yet enough because we want to really show that this is really more likely. We need a little bit of a boost, but this is kind of the main idea. Questions? Okay, so once you have this this inequality for these edge sequences, now it's kind of a matter of putting things together. Because remember, when we look at what's the probability of getting a certain graph, you can sum over all possible edge sequences. You regroup them in a suitable way that you can apply this inequality from the previous slide that we established. And that allows you directly to compare the probability of getting one graph with the probability of getting the other graph. Okay. Just expand things out, regroup them, and apply each time this inequality. Of course, this does not yet prove really what we want, right? Because we want this guy is really more likely. And the trick is that we cannot prove that for each of these edge sequences there's a difference, but you can prove that in this super large sum, there are many terms where you win a little bit, and that's enough to give you this extra 1 plus epsilon boost that we need to show that this guy is really more likely than the other one. All right, so now comes the part which is more similar to classical switching, which you asked about how this works. And so here, what you do is you set up some auxiliary bipartite graph. You put just up here all graphs where the number of these 1, 1 edges is L plus 1, and down here where all of them is L. And then what you do is you connect two of these points, which each correspond to graphs, if there's a way to do switching from one to another. Okay, this defines you some nice bipartite graph. And the key point is, and this really happens in all these applications also when you study random graphs of the given degree sequence, is here that in a certain regime, this auxiliary bipartite graph will be approximately regular in the sense that all the degrees up here are roughly the same and all of them down here are the same. But I mean, the degree up here and down here can be different, but all of them are kind of the same. And that means that if you have in such a situation, you can lift an inequality from one graph to a class of graphs that you're comparing here, right? Beforehand, we just had an inequality. One graph in here is more likely than its switching partner down here. But because this auxiliary structure here is so regular, you can actually lift it now to this class of graphs. It's a kind of a double or weighted double counting argument, which underlies this kind of argument. Again, the point is, we never need to calculate what is actually the probability of any trajectory. We always look at ratios. So once you have this for these classes of graphs, it's just a matter of finishing off by some careful arguments. Basically, our goal was to show that you're not very close to this mu, which is the expected number in the configuration model. And now the idea is to kind of look at some telescoping product. So you each time compare what is the probability of seeing deviating z from the mean versus z plus 1 from the mean. And if in each time you gain actually some factor 1 plus epsilon, then because here you're deviating so much from the mean, this epsilon mu, which is kind of linear in n, you actually can show that the probability of landing close to the expected value in the configuration model is super tiny. It's exponentially small, actually, in this model. I know these arguments are a little technical, but the main point is once you have it on the level of graph sequences or trajectories of the process, you can lift it sequentially to the properties we're interested in. Okay, and that's something that we found very interesting because we have not seen any examples of the switching method applied to stochastic processes, and so I think there's a lot of potential there to use that. So some of you might now rightfully ask, so what about the more general case? This was just for 1-1. Oh, yes?
So it's related to Dan's question.
Yes, so this argument here was just for simplicity. I proved that you're not in the middle. Oh, sorry. The question was that whether we can really prove that this process is here on the right. Okay, and the answer is yes. It just turns out that the argument I showed you here does not work in general. You need to do a little bit of extra because this comparison argument that this auxiliary graph is bipartite, so regular, only works when you're very close to the expected value in the configuration model. So you need a little different argument, but it's actually much simpler to show that it cannot be too small, turns out.
So are you going to show us the thing about how taking this eliminates? I'm sorry. So the individual switching argument, I take it that that's because the two vertical edges, or sorry, no, the horizontal edges eliminate more edges that are allowed by the degree sequence than the two vertical edges do, or at least, and so that there are, with fewer allowed edges, you're more likely to get the other horizontal edge or something.
So you're referring to this?
Yeah.
So okay. So the story is actually this inequality is not true if you don't look at 1-1 edges. So.
Well, okay, but I mean, just this example is.
Oh that... yeah. So there it's true because once you put down this thing of 1, then you're kind of done. You're doomed. This can no longer be chosen. So it turns out to be better if this happens early on in the process. And I would say that there are certain heuristics that we had for this case. But all of them, or the majority of them, all broke down when we go to the more general case. So it's a little hard to reason about the case where the argument is not generalized. So it's a little bit tricky. So we first thought all of this would go through to the general case, but then my student came up with some counterexample, and then it was quite tricky. So basically, what happens is that also when you allow for larger degrees, also what happens in your neighborhood somehow starts mattering. It's quite tricky what happens with these probabilities. I wished really there was a simple reason how to reason about it. Okay, so let me just say that this approach, you can try the same. So now we need to find some replacement in the general case. What does it mean? What is the replacement for a 1-1 edge? And so here you say there's a vertex is called small if the degree is at mode S. And what you want is that there's a reasonable amount of small edges, again, between say 1% and 99%. And now you want to count how many small edges are there in this process. And again, you want to prove that the number of these small edges is different what the process generates and what the random guy generates. Okay, so again, you see how you arrive at the graph matters. And as I already alluded to, unfortunately, some of these key inequalities fail. So I mean, what was underlying our heuristic that this graph with more 1-1 edges should be that if you do some kind of switching, that then you win. Okay, so here in this case here, here you would look at kind of this point here. So this corresponds here to a vertex of degree 2, and this corresponds to a vertex of degree 2. So that would be a small here because we have vertices of degree 3. And when we do the switching of this guy here compared to with this vertex down here, then what happens is that this graph is actually less likely than this one. So it kind of goes, it's not just fails a little bit, it fails completely, right? We want to prove it's at least 1 plus epsilon, and it's actually only 0.82. Okay, so this idea of looking at graphs no longer works. And so this example was kind of surprising because it's ruined all the intuition we had built up beforehand. But there's a way around, and I will not go into details how this works too much. But the idea is, instead of focusing just on graphs, you find some clever way how to regroup the graphs. So that if you look at graphs in one group and compare them with graphs in the other group, the inequality still works in the correct direction. Okay, so it's kind of like instead of doing this switching idea on individual graphs, you do it on groups of graphs, which are very carefully chosen to make this argument work. That's maybe what I want to say about that. So let me maybe otherwise summarize. So we looked at this degree restricted process where we started off with an empty graph on n vertices. And in each step, we kind of put down a random edge without violating this degree constraint. And then the main question was, is this similar to a uniform random graph or not? And the main story was that if the degree sequence is not nearly regular, so if no vertex appears more than 99% of the time, then we can actually distinguish these two graphs in a very strong way. I give you an explicit edge statistic that you can calculate in polynomial time. And based on that, you will be able to say with high probability, does it come from this graph or this graph? In fact, what our argument also shows, let me just mention that, is that if you look at the total variation distance between these two guys, so we had once the process and once the uniform graph, what we can show is that the total variation distance is extremely close to 1 in this case. So it's actually exponentially close to 1. So it's really, really nearly maximal. And also our argument shows that if you want to go from the graph that is generated by this process to the graph generated by the uniform graph, you actually need to change at least the linear number of edges. So they're really, really far apart in terms of how to go from one to another. So what was one interesting thing here? I think one interesting thing was the proof technique that we used, because this idea of using the switching technique to analyze stochastic processes, that was kind of a new idea. And I hope that this has some more potential. And I do want to mention in terms of open problems, I do believe that when you look at regular degree sequences, I do believe that these two are same. So I'm kind of with Wormald there on the same page, that somehow it feels that they're really so close, whatever at least what we try to look at and so on, it's really hard to have any idea what's going on. How could they be different? So that's, I really think it would be an interesting problem to show that actually these are contiguous, they are similar for regular degree sequences. And I do want to mention that I particularly believe the two regular case has some potential for maybe one can do something. So note that for two regular case, you're just looking at the collection of cycles. So this is like as simple as it can get. So there should be some way how to prove things. And the closest maybe to show some similarity, like really close similarity between these models is that we know of is with respect to the giant component behavior. So if you look at, for example, the two regular case, when you look at this, this process plus the uniform one, so let me say two regular, say, process plus uniform, they have the same behavior in the following sense, that if you look at the two regular random graph, you do not have a concentrated giant component. So it's a little bit different than the classical Adler-Schwenny theory. So what the result looks like there, you get is that the size of the largest component, and so here you can put in either of these two things, either the process which generates it or the uniform one. And you look at what's the probability that this has at least size c times n, then in both models it converges to the same function f of c, where this function f will be between 0 and 1. So this is I would say the closest thing that we know where these two models behave very, very similar. Okay, but we're still the arguments we use here are still not fine enough to prove anything like contiguity or total variation distance or anything like that. Okay. So you still have a little bit of wiggle room because of the error term and so on and so forth. But I do think that this is some further supporting evidence that most likely it's actually true for these two regular degree sequences. So I think that would be a really nice problem to show that they're similar, or I would be really surprised if they're different. Maybe that would be even more interesting. I mean, locally, you will just see like some tree right at the end, so deregular tree. So you need some kind of more global statistics, but I don't know if you really want to distinguish them, how that would look like. That's kind of the question, like what statistic to look at and how to actually prove that they're different. For example, you might look at the eigenvalues and so on, but then it really becomes a little tricky. How do you calculate? Okay. I'll open up just for more questions.
Okay, do you have more questions?
Of course, your final example here raises the question whether the giant is different in the degree irregular cases, right? I mean, you can prove that the two laws are very different, but are the sizes of the giant also very different?
So
you would believe so, but
and if you go to larger degrees, then they're connected at the end, right? So it's kind of a slightly different story. What I can tell you is you can study.
No, but he didn't mean, sorry, but he didn't mean degree at least 3. He meant that you have some degree distribution, but it's the lowest degree is still 2, let's say.
Yes, okay. So we have studied this giant component question, but not necessarily at the end. So we kind of studied the giant component phenomenon when it actually happens, when it starts emerging. And it happens that for the interesting case, it happens before the end. So you see the giant already emerging before the end. And there, what I know based on simulations is that the distribution that you get seems to differ from the configuration model. So what we did is the following. So we kept track of the degree sequence of the process at any point in time. And then we plug that into Molloy-Reed. So you can kind of ask Molloy-Reed, when would Molloy-Reed tell me that there's a giant? And then you can ask, when does it actually happen in this process? And they happen at different times. So it's kind of a strong indication that early on, these two guys are different, but that still does not rule out at the end, they still have the same distribution. I wish someone can prove that they're different. I think it would be really interesting.
Other questions? Okay, who is the next speaker?